Hello and welcome back to part 2 of the ASHTAS Operative Training video. We now move on to Module 3, System Performance, which includes barrier selection, barrier performance requirements, standards, test criteria and containment levels. The following is a video that was produced by a layperson who wanted to understand how barriers have evolved, how they work and why there are different types out on our road network.
I used to think driving was getting more and more dangerous, and one reason is the media loves to sensationalize car accidents.
Multi-car pileup in North Texas has killed at least 6 people. Incredible.
And with those kind of stories, I was surprised by how the fatality rate has steeply dropped over the decades, even with more drivers on our roads today. We save more lives because of better seatbelt enforcement and catching intoxicated drivers. Cars are also safer with crumple zones, airbags, and ABS brakes.
But did you know we've greatly improved the design and engineering of road barriers in the last 60 years? Like this connection between a guardrail and concrete barrier.
In the past, vehicles used to be crushed, but now they gracefully bounce off, and I'll tell you why later. We also removed these terminals from highways, which in the 60s made you look like a hot dog, and replaced them with something far safer.
My name is Andrew, and let's uncover how good road barriers have gotten to save more lives.
Roadside safety equipment is made by different companies, and their products undergo real-life crash tests to prove their products work. In the United States, that standard has gotten more rigorous over time, and the latest is MASH, or the Manual for Assessing Safety Hardware. Compared to the older 1998 standard, MASH uses heavier vehicles, faster speeds, and higher angles. MASH-rated equipment has to be built better to handle the much higher impact forces.
In this video, I'll be focusing on MASH and how it's made our roads safer.
MASH-rated products have 6 safety ratings. The lowest is TL1, with higher ratings requiring products to stop heavier vehicles at faster speeds. The highest TL6 barriers that can stop tanker trucks are massive structures and rarely used on our roads today. For each level, all equipment has to pass 3 tests. Number 1, it must keep the vehicle upright with no rollovers, which can cause severe injury to occupants, which means this product would fail and would need a redesign. Number 2, the vehicle can't tip more than 75 degrees or go over the barrier. That means this barrier does not pass MASH testing. Number 3, there could be no penetration or crushing of the passenger compartment, and impact forces must be below the maximum allowed. All of this data is recorded and analyzed to figure out if a product fails or passes.
MASH-rated equipment has been mandated for new installations like this concrete barrier, and is an important part of the safety system.
Barriers prevent vehicles from driving into hazards like buildings, bodies of water, and oncoming traffic. But crash barriers are themselves a danger. They're longer, closer, and easier to hit, which increases the number of crashes, even though severe injuries and deaths are greatly reduced. It's far better to have vehicles run off the road into a safe area of land called the clear zone, which allows drivers to recover or reduce the severity of a crash. Engineers can create clear zones by removing hazards and grading the land according to guidelines, which covers things like the steepness and the width required. But it might not make financial sense, or it's not possible to create a large enough clear zone, which is when barriers can be used.
This chart is the crash types of fatal crashes between 2016 and 2020. Looking at this chart, unfortunately, the highest percentage of fatalities are run-off road accidents. This is why in recent years a great deal of funding has been allocated for barriers to be installed along our road network. And if a vehicle hits a barrier, we need to ensure it will function as designed, and this is why barriers need to be installed as specified. The SAFE system takes into consideration that drivers unfortunately do make mistakes. The SAFE system looks at safe speeds, so in other words, lower speeds around schools, shopping strips, roads with unprotected hazards, etc. Safe vehicles, the safety improvements to vehicles is continuing to improve, and safe road users, getting drugged and drunk drivers off our roads and enforcing the law, making sure road users are operating in a safe way. Then we have safe roads and roadsides. This is the area, as road barrier installers, we can make a difference by ensuring that the approved barrier system is installed as stipulated and to the manufacturer's specification. A quality barrier installation for a better outcome if an errant vehicle hits the barrier. Using the safe system approach makes the road network more forgiving if a driver does make a mistake. Crash testing is as old as myself. The testing process has evolved since 1962, and the current test standard is MASH, Manual for Assessing Safety Hardware 2016. Worldwide, there are two current testing regimes for barrier systems. As I mentioned, MASH, that's from the USA, and EN 1317 from Europe. The road environment in Australia reflects the environment in the US, so therefore MASH is used as our testing standard. This is specified in a previously mentioned ASNZ 3845-2015 standard. Some older barrier systems were tested under a previous assessment process, NCHRP 350, the predecessor to MASH. The continued acceptance of these is with each local road authority. So therefore, some products may have been tested under NCHRP, but are still accepted by a local road authority. Each road authority does have documentation that will have what are accepted products, what are discontinued, and what products should not be used. Systems you work with may have been tested into both standards, but again, only MASH tests are recognised currently. So why test? The test provides real-time evidence of performance based on speed, angle of impact, weight, and the critical impact point, the CIP. The road authority will identify what protection is required using road traffic data, which includes accident, incidents history, types of vehicles, volumes of vehicles, future road usage, hazards requiring protection. It does not mean that 100% protection from a hazard. For example, if there is a high angle impact or a vehicle is travelling very fast and impacts a low containment system, they may not work. The test also sets the installation standard, noting the system will not work correctly if not installed correctly. As mentioned on the previous slide, we looked at the critical impact point, the CIP. The critical impact point considers both the weakest part of the system, this may be a joint or the middle of the rail between two posts as examples, and the strongest points of the system, the point where the system does not move, in addition to all other sections of the install. It is the CIP that is tested to ensure the safety of the road user. As shown in the table, there are 6 different test levels for barriers. TL1 to TL6, test level 1 to test level 6. Test level 1, 2 and 3 only uses passenger car of 1100 kilograms or a pickup truck or ute of 2270 kilograms. Under the TL1, the approach speed is 50 kilometers an hour and the angle of impact is 25 degrees. And there you move to TL2 and 3, which same vehicles, higher speeds, same impact angle. Moving into TL4, they use a higher weighted vehicle, and in 5 and 6, again, they use a heavier vehicle at different speeds and different angles of impact. TL1 and 2 would be used for residential or urban environments, TL3 for freeway, expressway or motorways, and TL4 to TL6 also include the truck, as I mentioned, in addition to the small car and pickup. This is where the barrier is designed to provide asset protection for example, a bridge pier. The road authority will specify the required containment for an installation. Moving on to terminals and crash cushions, and without going into a lot of detail about the tests required for these terminals, as you can see, there are 7 tests required for a terminal compared to 2 for a longitudinal barrier to achieve a TL3 classification. There is a high cost for a proponent to undertake this testing. There are 8 different tests for crash cushions, and again, this is a high cost for a proponent to undertake this testing. This testing is so important to ensure a product will perform as required. Under the MASH testing standard, recognises 3 criteria for evaluating the safety performance of roadside hardware: structural adequacy, occupant risk, and post-impact vehicle response. Structural adequacy, the test article contains and redirects the vehicle. The vehicle should not penetrate, underride or override the installation, although controlled lateral deflection of the test article is acceptable. Occupant risk, detached elements, fragments from the test vehicle or article should not penetrate the occupant compartment or present an undue hazard to other traffic or bystanders. This also establishes the acceptable occupant impact velocity, the amount of G-force experienced by the occupants. And then you have post-impact vehicle response. After the collision, it is preferable that the vehicle's trajectory not intrude into adjacent traffic lanes. So in summary, MASH is the current approved test standard for road safety hardware in Australia and New Zealand. The difference between test standards 1 to 3 and 4 to 6 is angles of impact, speed, and vehicle type. The critical impact point considers both the weakest part of the system and the strongest points of the system. The complete list of parameters the Austroads test standard considers are weight, speed, angle, and direction of impact. Module 4, terminology and install requirements. Look at road design terminology, barrier system types, and install requirements. Road design terminology. And noting, definitions marked with an asterisk are taken directly from the Austroads glossary of terms. Carriageway, that portion of a road or bridge devoted particularly to the use of vehicles, inclusive of shoulders, sealed or unsealed, and auxiliary lanes. Single carriageway, traffic flows in both directions and are not separated. Dual carriageway, opposing streams of traffic are separated by a median. And median, a strip of road not normally intended for use by traffic, which separates carriageway for traffic in opposite directions, usually formed by painted lines, curbed and paved areas, or grassed areas. Expressway, a road mainly for through traffic, usually dual carriageway, with full or partial control of access. Intersections are generally grade separated. Freeway, a divided highway with no access for traffic between interchanges and with grade separation at all intersections. Motorway, a divided highway for through traffic with no access for traffic between interchanges and with grade separation at some interchanges. Certain activities or use may be restricted or prohibited by legislative provision. Moving on to some barrier terminology. System width, the front to back dimension of a road safety barrier, including its supporting posts, etc. Dynamic deflection, the largest transverse deflection of a barrier system during an actual crash. The distance between front face of barrier system before impact and the lateral position of either the barrier or the vehicle during or after impact. Continuing on with barrier terminology, Vehicle roll allowance. The lateral distance between the deflected face of a road safety barrier and the maximum extent of a vehicle body roll during impact. Working width. The minimum width that is required to prevent an impacting design vehicle from colliding with an object behind a barrier system. This includes both the dynamic deflection of the road safety barrier, if any, and the extra width to allow for the vertical rotation of an impacting vehicle. An example of this is on the next slide. So the working width includes the dynamic deflection, system width, and vehicle roll allowance. This is measured in full-scale tests of a barrier from the furthest roadside element of the barrier to the furthest extremity of any part of the system or vehicle during and after the impact. So looking at this picture, you can see we have the system width, the dynamic deflection, then taking into consideration the vehicle roll allowance. This is your working width. Noting this barrier installation may not meet all the criteria as an acceptable barrier for this location. And finally, we look at design speed, a speed fixed for the design and correlation of these geometric features of a carriageway that influence vehicle operation. Design speed should not be less than the intended 85th percentile speed. The shoulder, the portion of formed carriageway that is adjacent to the traffic lane and flush with the surface of the pavement. A shoulder can be sealed or unsealed. Convex curve. A convex curve is curved towards the traffic line, and a concave curve is curved away from the traffic line. So in summary, dynamic deflection, the largest transverse deflection of a barrier system during an actual crash, the distance between front face of barrier system before impact and the lateral position of either the barrier or the vehicle during or after impact. Working width, the minimum width that is required to prevent an impacting design vehicle from colliding with an object behind a barrier system. This includes both the dynamic deflection of the road safety barrier, if any, and the extra width to allow for the vertical rotation of an impacting vehicle. The next part of the presentation is the continuation of the video, How Barriers Work.
These barriers come in 3 categories: concrete, guardrail, and cable.
You often see concrete walls like this one. While it seems simple, there's some surprisingly well thought out engineering.
If you look at their profile, many aren't vertical but sculpted to reduce crash forces. One hit, your vehicle rides up the slope surface, and this vertical motion dissipates energy, which reduces vehicle damage and impact on occupants. Unfortunately, this lifting motion can cause the vehicle to roll over under high speeds and impact angles. To improve this, engineers tested many shapes, and while the New Jersey barrier is popular, single slope and F-shape are better as they don't lift the vehicle as high, which increases stability and prevents rollovers. In comparison, vertical barriers minimize upwards movement. They're often used on bridges as you don't want vehicles to be catapulted over the sides. Unfortunately, that increases impact forces and wheel damage, which can cause the vehicle to veer sharply into traffic. As well, higher lateral forces can push your head through the window, which can cause head slap and greatly increase your chance of dying. For those reasons, you mainly see slope barriers on highways today. Concrete walls are often used where you can't have any movement, for example, if it's close to a hazard. When there's more space, you'll often see a semi-rigid system instead. These can use a box beam, or more commonly, you'll see a flat corrugated guardrail connected to a wooden or metal beam for support. These are driven into the ground and often use a strong post system, which is quite ingenious. When hit, the posts rotate outwards and down, transferring kinetic energy through the soil, which reduces impact forces. As well, the rail detaches, so it stays at the right height and in contact with the vehicle, which also prevents tearing. On older designs, the rail is more likely to remain connected and can rip, letting the vehicle through. This tearing can also happen if the post can't easily rotate, which pulls down the rail. The new, safer MASH-rated guardrails only use a minor height increase and connection change versus the older rail to better contain heavier vehicles and prevent taller ones from jumping over the guardrail. It's also likely there's an offset block that keeps your wheels from snagging. This helps the guardrail improve stability and reduce sudden impact forces on occupants.
Remember this guardrail and concrete connection I mentioned earlier? Engineers figured out they needed to add extra posts to prevent vehicles from being crushed.
If the connection between the two is not reinforced, the guardrail bends and tears, with the vehicle smashing into the concrete face with horrific outcomes. Engineers added posts to stiffen the connection and allow the vehicle to bounce off as it was designed. Finally, we have cable barriers that are placed in medians to prevent vehicles from flying across and striking oncoming traffic. These have existed for decades, as you can see in this 1930s Missouri transportation video. Modern systems use 3 or 4 cables to safely catch vehicles and are under high tension to withstand multiple impacts and reduce movement.
To pick the right system, engineers weigh factors like traffic, volume, vehicle types, and landscape.
Barrier system types and considerations. Rigid, semi-rigid, flexible. Rigid systems have a higher impact severity, higher vehicle damage, contains a higher energy impacts, low system deflection, however reduced maintenance, but may require rebuild if damaged. Rigid systems are normally made of concrete. This may be reinforced precast concrete elements or unreinforced extruded concrete installations. Often provides the best protection for high energy impacts from large vehicles, requires little or no maintenance. A minority of steel systems may be classified as rigid, but please refer to the Road Authority approvals. May be used for both temporary and permanent applications, if approved again by the relevant Road Authority. The following video demonstrates how important rigid barriers are to ensure an errant vehicle does not cross onto the other lanes of traffic travelling in the opposite direction. Semi-rigid or deformable non-rigid barrier. Semi-rigid severity of impact is often less than rigid system, often less vehicle damage, and it is post-system dependent. And due to the system design, both post and rail may require replacement. On impact, the system deforms and often requires replacement due to deformation. The system deflects and therefore suitable clearance to a hazard must be provided. May be made from steel or precast concrete. Most common systems are corrugated W or tri-beam. Some freestanding system, concrete/steel, can be used for temporary applications, again if approved by the Road Authority. Flexible barrier systems. Often lowest impact severity. Due to low impact severity, sometimes minimal vehicle damage. Often has larger deflections when impacted. Generally are wire rope systems, require greater space between the hazard and installed system. The system is mounted on post, simple to repair, often only requiring a post replacement. Due to the nature of construction, these systems are generally not suitable for temporary applications. They are the most forgiving system for occupants, the lowest deceleration values, lower install costs, and lower repair costs. They also are a narrow system width. There are limitations with this type of barrier. Large deflection area is required. Minimum 200 metre radius, minimum 60 metre length, but ensure you refer to the manufacturer's specification for these distances and lengths. They are easily damaged, not compatible with motorcycle rub rails, and they do require a rope tension maintenance regime. So in summary, rigid systems, a road safety barrier where there is no observable dynamic deflection during a vehicle impact. The deformation is contained within the impacting vehicle. Normally made from concrete, this may be precast reinforced concrete or unreinforced extruded concrete. Semi-rigid or deformable systems are normally made from steel, may also be produced from precast concrete or combination systems, steel and concrete blast. Flexible systems are generally wire rope. Types of road safety hardware that have a low dynamic deflection / working width for placement close to hazards are usually described as rigid or semi-rigid systems.